Thank you for the introduction. I now feel I have a lot of expectations to live up to. So I'm a researcher at AIST, the Tokyo branch, even though the bigger branch is here in Tsukuba. And I'll be talking about demonic dynamic logic programming. So I want to introduce how I got to studying this topic and how I got to proposing this new programming language. And so I want to start with something that probably most of us will already believe about the design of new programming languages. And something I think a lot of us already believe is that good logic ideas tend to be good language ideas. I put a picture of a robot assembly line because it almost feels like an assembly line, how any good idea in logic can be turned into a new language. If we're thinking of this functionally, we would think in terms of the Curry-Howard correspondence, that propositions are types. So if you take predicate logic and you put it in the assembly line, you get dependent types. If you put second order logic, you get polymorphism. If you put classical logic, you can get continuations. If you put affine logic, you can get ownership and the Rust type system. But a similar story can also be told for logic programming languages, and this is a logic programming language paper. But it's a slightly different story because it's not Curry-Howard, it's the programming as proof search correspondence, the idea that searching for proofs is executing a program. And so if we put predicate logic in at one end, we get out Prolog on the other side. If we put in higher order logic, we'll get higher order abstract syntax. If we put in temporal logics, we get a few different languages, but some of them are good for things like real-time systems. And if we put in linear logic, we can get logic programming languages for concurrency. And I looked at this pipeline and I realized that my favorite logic in the whole world had never been put into this pipeline. And that made me really sad. And so my favorite kind of logic in the whole world would be program logics. This paper specifically uses a style called dynamic logic, but dynamic logic is maybe not as well known as the others. So I say program logic to make it general. If you're more comfortable with, say, Hoare logic or Dijkstra's predicate transformer presentation, these are all doing the same kind of thing as each other. And what this paper is trying to answer is if I put this in the assembly line, what programming language will come out the other side? And what can I do with it? And before I answer what that language is, I want to take a moment to ask, why is this still an open question? Because it feels like it wouldn't be. So we've had Prolog since the 1970s. We've had temporal logic programming since the 80s. We've had higher order abstract syntax since the 80s. And we've had linear logic programming since at least 1992. And that's not as old as Prolog, but it is older than me. And so that's not the end of logic programming. There have been new languages developed in my lifetime, but there's been very little on programming logic as a logic programming language. And I argue that a few different things need to happen before this story could be told. So first, we need to have a clear picture of what the computational content of proofs will be. If we run a Prolog program, we know what kind of data that's giving us back, what kind of computation it's doing. We need the same story for program logic. And I might not be the only person that studied this, but some of my work about 6 years ago really helped build the foundation for the work I'm showing you today. We also need to know what the applications are going to be. As I'll show you in another slide, I'm going to argue that reactive synthesis, synthesizing code, is one of the main applications here. And that's not only 15 years old, but a lot of the work that really made this as big as it is today was only in the 2010s. And there's also a very fine balance we need to strike, where proof search needs to be automatic enough that we can really think of this as a programming language, but still expressive enough to say something interesting about a program. And that balance is really what this paper is trying to do. And so I also want to take a moment to sell for maybe the less theoretical people in the audience, what can we do with this when it's done? Now, this is the first paper I plan in a series of at least 3, so the examples are going to be a little smaller today. But here's the long-term mission. So dynamic logic in particular is about non-deterministic programs. And what a proof does is it resolves the non-determinism. So today we're just going to look at this first part. We're going to look at box formulas that talk about postconditions that hold for every possible behavior of a program. And that's kind of limited computational content. It's kind of the same content that a for all quantifier or a conjunction might have. But the next step of this is going to be the propositional fragment, where we have diamonds. And diamonds do something interesting because they say there exists a behavior of the program that makes the post condition true. And so what that proof is really doing computationally is it is selecting among many possible behaviors to pick one that makes a condition true. And all of a sudden, that's solving a synthesis problem against some specification. If you put these two together, you get game logic, where we can say things like, for all behaviors of alpha, there exist behaviors of B that make the post condition true. And for anyone that has some bit more synthesis background, this is exactly how reactive synthesis problems are stated. For all things an opponent does, there exists a response that achieves the condition. And so the goal in taking this logic programming approach to the synthesis problem is to kind of overcome some of these scalability challenges that are very fundamental to synthesis in general. Many synthesis problems are undecidable, but what languages are good at are taking a large program we want to write and breaking it down into many smaller pieces. And so having this inside of a language might give us a way to take a larger synthesis task and break it down into kind of a stage-by-stage task that's easier to solve. So that's where we want the work to be in maybe another 2 or 3 years. Let's talk about where it is today. And to do that, I'm going to start digging into the background material and the proper syntax of the language. The background is a logic called dynamic logic. And so for those who were raised with Bohrer logic or predicate logic as their first languages, I have a translation on the slide. There are 2 main syntactic classes in dynamic logic. We have programs, alpha and beta, and we have formulas, phi and psi. And a slight difference between your standard Bohrer logic is there's more focus on non-determinism. And so we're going to have the regular expression operators as our main program constructs. You can have a constant program C. You can have a choice program that does anything alpha does or anything beta does. You have a sequence that does anything alpha does followed by anything beta does. You have the assertion that works like a no-op if phi is true, or does not run successfully at all if phi is false. And we have loops, but loops are also non-deterministic. So alpha star says repeat alpha any number of times, including 0, but it must be finite. And then once we have this basic programming language, we can come over and we have our formulas as well. We have all of the propositional operators too, but the box formula is going to be our focus today. It says for all possible behaviors of alpha, in the final state of alpha, the post condition phi is true. And then diamond, which is the next paper, says there exists such a run. And setting things up this way gives us a very clean cryptic semantics for the programs. We can define a program as a transition relation from start states to final states, and we get a very nice algebra to it. So the choice operator is really a set theoretic union and so on. For formulas, we can have the set of states where a formula is true. This works very standard for, say, or and so on. And then the box formula, again, the star of today's show, it's the set of all initial states omega, where I can transition from omega to nu, such that nu makes the post condition true. If your native language is Bohrer logic, then we could take, say, a partial correctness specification of Bohrer logic, and initially phi, and then after alpha psi, and this would turn into an implication. So initial condition phi implies box alpha psi. Likewise for predicate transformers, likewise for total correctness assertions as well. If you have a non-deterministic language, it's a bit more subtle than this, but if it's a deterministic language, then these truly are equal to each other. Okay, so I want to give an example of the kind of things that can be modeled in this language, despite being a relatively simple language. And the example used in the paper is what we call a pursuit evasion game on a graph. And so this is a game between 2 players, Angel and Demon, and they take turns moving around the vertices of some graph. And so Angel wins the game if Angel ever reaches the same spot as Demon, and Demon wins the game if the Demon can forever evade the Angel player. And it's a little bit tricky to encode the state of the game, but we're going to do that using propositional formulas. So each propositional formula is a complete game state, For example, this AC means angel is at spot A and demon is at spot C. And what this first formula says is if I take the move of demon moving left, now the angel is at state A and the demon is at state B. I don't expect you to read every single equation, but I want you to give a sense of how you put these building blocks together to build an example. So the first two lines are really specifying out what the basic moves even do. If I'm in this initial state and I take this move, I end up in this following state. The third line, defining demon turn, is laying out what are all the options available to the demon player. Right? And so I can either go to the left or I can go to the right. And then for the angel player, the first two lines of angel's code are very similar, just laying out if I go to the left as an angel or I go to the right as an angel, what is the next state of the system? But because demon and angel are doing different things, they're different players, if we encode this in propositional dynamic logic, we're going to get a little bit different way of writing this for the angel, because we have to react to the demon's moves. So only if I'm in this state, or only if I'm in certain states is it safe to move left, and only if I'm in certain states is it safe to move right. But I'd argue perhaps the most interesting part is the final line, which is the query. So in Prolog, we often do something a little bit more computational with our queries. But this is an example where it's really this traditional interpretation of logic programming almost as a kind of theorem prover. So the example query says if I start in state AC, then I repeatedly let the demon take a turn followed by the angel. And as I do that, this invariant formula will hold at every state, and that same invariant will hold at the end. Now, this particular invariant says that the two players will always be at opposite positions of the graph. If you try to work through a winning strategy for the demon player, just staying as far away as possible is the best strategy, and so staying in the opposite node is optimal. And so what this language allows us to do is to write these relatively complex invariant specifications as our queries and check them fully automatically once we've spec'd out the contents of the system. All right, and so in general, any kind of invariant property like this of a finite stateful system is something we can specify fairly straightforwardly. But if we have a rich logic for queries like we do, then we need to be very careful what kind of syntactic restrictions we have, because we can't let this get so complicated that proof search become impossible. And so the logic program itself is structured as a series of declarations and a query. Declarations can either explicitly define a symbol, they can have more Prolog style specifications, and they can also define box formulas. A query is just a goal formula, but we need to be careful defining what the classes of clause and goal formulas are. We do this in a similar style to Miller's presentation from the higher order abstract syntax work. But in general, you tend to want to rule out some of the more complex formulas when they're serving as a clause. So when they're in kind of on the left-hand side of a turnstile. And so what we're going to say is that we rule out disjunctions, which is almost a standard choice. Prolog does the same thing. But we also need to talk about what clause and goals mean for programs, not just for formulas. So we're going to rule out repetitions when they're in a clause position because there's just too much non-determinism in the proof search otherwise. On goals, on the right-hand side of a turnstile, however, all of the operators are allowed. You're allowed to have repetition. You're allowed to have disjunction. One thing we require in the syntax is that even in a goal formula, loops always need to have invariant annotations. And we do this so that this can truly be logic programming as proof search. There are algorithms to generate invariants, but at that point, it's a much more model theoretic approach. It's not really just doing a simple search anymore. But we then need to ask what kind of formulas are even allowed in invariants. And in summary, the invariant formulas and invariant programs, they have to satisfy all of the constraints for both goals and clauses at the same time. So it's a little bit more restricted class. And if you're not sure why this is the right syntax to have, I want you to hold that thought because we're going to prove that as a theorem in a few slides. So I've specified what programs we can even write, but how do we decide what our program should even mean? Taking this traditional interpretation of programming as proof search first before anything else, we're going to use a sequent calculus as our proof theoretic semantics. It's going to be a constructive proof sequent calculus, so there's only one formula on the right. And a lot of the rules that we start with are going to look like very standard rules from predicate logic. Okay, so we have rules that say things like, if the formula is true from the context or it's true from the signature, then we know that it's true. We have things like, I can expand definitions that are defined in the signature. The signature, by the way, collects all of the rules of the logic program, so we can use these rules throughout proof search. And we have a lot of standard propositional reasoning as well. So if you want to prove a disjunction, you pick a branch and prove the branch. If you have an assumption of a conjunction, then you can assume both branches. And all of these look like the kind of proof rules that you would already have in, say, Prolog or in Lambda Prolog. There's nothing too shockingly new just yet. But we also need to handle dynamic logic. And so this is where we need to be a little bit more careful. The first three rules on this slide, I would say, are standard for dynamic logic. The last one is not standard even for dynamic logic. One of the kind of key technical details that makes DL a little bit different from Bohr logic is that we can nest the modalities as much as we want. So if I want to prove alpha, then beta, then post-condition phi, I can actually write this as a nested modality. After alpha, it is true that after running beta, phi will be true. It's a nice technical trick we can do. And these next two aren't so bad because choice just works like a conjunction. It needs to be true both if I run alpha or if I run beta. And it might not sound like it from the description, but a test really works like an implication because we need to hold for all transitions. And if the test fails, there are no transitions to quantify over. If the test succeeds, we need to prove, we get to assume that the test passed, and we need to show that the post condition holds in the same state. The most technically advanced is the invariant rule. And this is all coming back to kind of the design of these syntax restrictions. It's kind of very traditional to want to ban disjunctions on the left-hand side. But if you look at the systems you would want to prove, almost always our invariant is going to be case by case. If I'm in this state, I have this invariant. If I'm in this state, I have this other invariant. And so we need disjunctions, but we don't want them to appear in formulas. So we build this in as kind of a special case in the rule. We build disjunction into the rule. And so initially, some branch needs to hold. And no matter which branch holds, if I run one more step, some branch of the invariant should hold. And for any branch that holds, it should apply the post condition. And so that in some sense, this is a very standard way to reason about invariant, but we have to be careful about these technical details. Unfortunately, this is not quite the end of the story. So let's think about a very simple kind of program, which is a program that has a semicolon in it. So imagine I want to run C1 followed by C2. And I've defined both C1 and C2 using some predicates in my source code. So maybe C1 leads to state Q1, and from state Q1, C2 will take me to state Q2. I should be able to run the query C1, C2, Q2. But after one step, what I'm going to get is this nested modality. And none of these rules above explicitly tell me how to handle a nested modality. I need some sort of either maybe some sort of substitution principle or some sort of contextual reasoning principle to make this all work. And the way that I approached it in this paper is by adding monotonicity rules to the picture. And so monotonicity reasoning says, it comes up in a few different forms, but I think the easiest one to start with is that if I want to show that psi holds under a box, I can show that phi holds instead, and show that phi implies psi even in the empty context. So forgetting everything I know and just proving it from scratch. And as soon as I have any of these monotonicity rules, now I'm much better equipped to reason about potentially nested modalities, or also known as programs that have a semicolon. It's a very rare class of programs. Yeah. And so this is going to be enough to define the proof theoretic semantics. But this is already starting to hint if we need some of these monotonicity rules, and these are much less syntax directed. This is a much more flexible rule than what we had earlier. Then the actual search process, the actual operational reasoning might be a little bit more complex than we first expected. And indeed, there are many rules in the operational semantics, so I've put most of it in the appendix, but I just want to give you a few examples so you can see how the operational semantics is structured. The way the operational semantics is structured is that at runtime, our state is just a formula or a collection of formulas. It's a collection of all open goals. And each open goal has some assumptions and some goals. So if you have, for example, something that's already proved, maybe something that is in the assumptions, then you can close a goal, you can reduce it to true, and then you can clean up the true in a separate rule. But in general, if you're doing, say, invoking some predicate C, or if you're doing any sort of program reasoning, almost everything has to work on the modalities. And so I write M here for not just one box, but any arbitrary chain of box modalities. These semantics do symbolic execution right to left, which means you're often reasoning deep under some complicated formula. And so so there's a little bit of work to require to show that this actually lines up with the first presentation. The good news is that we've done that work. And so we have a few theoretical results to put this together. And the first result is that everything is sound. Actually, there's two different ways that we want to show things are sound. First, we want to show that these operational rules are sound with respect to the proof theoretic semantic. And this is a long induction. There's a lot of different cases in the induction. But what this really comes down to is being able to put those core program reasoning rules together with all of the modal reasoning in order to get this extra flexibility. But there's a second kind of soundness, which is soundness with respect to the semantics of propositional dynamic logic. Because some of the rules I presented are not the way those rules are presented in kind of these standard papers on DL. There's all of this extra invariant reasoning and things like that. And so these are some long inductions, but to go into that, there are some extra stories that get told. So we have to make sure that, for example, that we designed invariant formulas correctly. And invariant should be both a goal and a clause, which it is. And as soon as we have these extra monotonicity rules, there's this question of what rules do we really need? Which ones are optional? So in there are some cases where monotonicity is required, but we can simplify it a bit. We can, for example, we can derive the rule G from monotonicity in most cases. All right. So that still doesn't quite answer everything. I didn't answer, for example, why I chose exactly the clause and goal formulas that I did. And so there's another important kind of test of validity. This also goes back to, I guess Lambda Prolog was kind of invented the style of proof. We want to show that the proofs resulting from proof search are in some sense well-behaved. And we do this by proving a property called uniformity. This is a very long theorem statement, but there's a much simpler way to state it. A proof is uniform if at every step, if the top level connective of the conclusion is the introduction rule that gets applied. So the proof kind of starts from introduction rules, and the introduction rules follow the structure of the formula all the way down. And this is not just an important way to test that we designed the syntax in a reasonable fashion. This tends to fail if you don't have the right syntax restrictions. But it also kind of tells the story of what the next steps will be as well. Because if you have a uniform proof, all of a sudden synthesis becomes much easier. It becomes much easier to read off code from proofs. So imagine that we've written the next paper, and this isn't just boxes, but diamonds as well. If I have a diamond proof that tells me which branch of the conditional to take, then I can look at the top level proof rule to say exactly what branch it is. Or if I have, say, I'm filling in a variable using a diamond proof rule, or I'm choosing how long a loop runs, all of these things will be things that we can read off directly from the top level of the proof, because the structure of the proof is exactly following the structure of the formulas. All right, so that's the results we have so far. I want to talk about the steps from here, and then we'll have a few minutes for questions. So in the paper, I do not claim the implementation as a contribution. And so I'm trying to be careful not to claim that as a contribution in this talk. But as I'm preparing the next paper, there's been a lot of implementation progress. It's about 2,600 lines of Rust plus equally many test cases. The example game I showed you on the slide solves in less than a second, maybe 300 milliseconds. And there are some libraries that come with it to make it easier to write things like games on graphs and also on state machines. So the future work has a pretty clear path laid out, that we want to extend this to all of propositional dynamic logic and all of game logic, build up the language implementation so we can really use it for synthesis, and then actually show that that works correctly. And hopefully this will not just be useful for solving games by synthesis, but as I was writing up the second paper, I also realized that this makes a really cute little tool for verifying finite state machines as well. So you can write a finite state machine as a series of rules, and then using the query language, you can basically write regular expressions, and you can test how any regular expression matches up with your state machine, which might be nice to explore as well. So that's it for the slides, and I'm happy to take any questions in my remaining time.